Hello! In this video, we're going to prove the following theorem. Let G be a group and suppose A is an element of G with infinite order. Then for all integers I and j, a to the power of I is equal to a to the power of j if and only if I is equal to j. Now, let's first remind ourselves what it means for a group element to have infinite order. It means the following. Given a group element A, to say A has infinite order means that there is no positive integer n such that a to the power of n is equal to the identity element. Okay, so now let's get into proving this theorem. Now let's just say that the identity element of our group is E. And from here, we want to prove for all integers I and j, a to the power of I is equal to a to the power of j if and only if I is equal to j. And since we're trying to prove a statement about every two integers, let's give ourselves two arbitrary integers. I'll call them I and j. From here, we want to prove that this is true if and only if this is true. And to prove a statement containing if and only if, what we want to do is we want to prove if this is true, then this is true. And we want to prove if this is true, then this is true. Now, one direction seems pretty obvious. It's pretty clear if I is equal to j, then a to the power of I is equal to a to the power of j. Because if I is equal to j, then we can take the expression a to the power of I, and we can substitute the I for j, since I is equal to j, so we get that a to the power of I is equal to a to the power of j. So now let's prove the other direction. We're going to prove if this is true, then this is true. And to do that, suppose a to the power of I is equal to a to the power of j. From here, we want to show that I is equal to j. And to show that, assume for a contradiction, we instead have I is not equal to j. To reach a contradiction, we're going to split this up into two cases. Either I is greater than j, or j is greater than I. Let's first consider the case I is greater than j. In this case, we're going to show that a to the power of I minus j is the identity element. And to see how this happens, we'll notice we know from properties of exponentiation, this is just a to the power of I times a to the power of negative j. But we know that a to the power of I is equal to a to the power of j. So this is just a to the power of j times a to the power of negative j. But then from properties of exponentiation again, we can just add the exponents. This gives us a to the power of 0. And by definition of exponentiation of group elements, a to the power of 0 is the identity element. So this shows that a to the power of I minus j is the identity element. In other words, we have that a to the power of a positive integer is the identity element. But this contradicts the fact that a has infinite order, because to say a has infinite order means that there is no positive integer that is able to do this. So this completes the case that I is greater than j. Now let's consider the case j is greater than I. In this case, we're going to show that a to the power of j minus I is the identity element. Now, from properties of exponentiation, we know that this is just a to the power of j times a to the power of negative I, but we know that a to the power of j is equal to a to the power of I. And from properties of exponentiation again, this is just a to the power of 0, and just add the exponents. And we know that a to the power of 0 is the identity element. So this shows that a to the power of j minus I is the identity element. In other words, we have that a to the power of a positive integer is equal to the identity element, which contradicts the fact that a has infinite order. So, no matter which case we have, we reach a contradiction. Our assumption that I is not equal to j led us to a contradiction, so we must instead have I is equal to j. And so we have shown if a to the power of I is equal to a to the power of j, then I is equal to j. So we have proven if this is true, then this is true. And we have proven both directions of the if and only if. So we have proven this entire statement. And we've proven this statement given two arbitrary integers I and j. Since I and j were arbitrary, we've proven for all integers I and j, this is true. And that is exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.